Hello there. So welcome back to our channel. Now we are going to design and simulate the operational amplifier based differentiation circuit. So we have a input signal that would be differentiated. For example, if we have a sinusoidal waveform, we'll have the cosine wave as a output, and the operational amplifier's role would be to add the gain to the output. So the expression for that, we can write it in this fashion. The output would be the negative of R times C dVi by dt. So in this expression, the R and C are the constants, and the derivative of the input signal will be produced. And to implement this equation, we need a circuit. So we will actually have a kind of circuit. As you can see, I'm going to draw that. So you will have an amplifier that is having two pins. It's a differential amplifier, and then we have the output. We'll have the capacitor at the input circuit, and in the feedback path we will have the resistor R. This is C, and that's here is your input signal Vi that will provide the current input current II, and the positive input is connected to the ground. And we have seen through the analysis, the output of this circuit comes in this form of equation. So now it's time to implement this circuit. So what we will do is to design this circuit, we'll pick up the components library. So let me do that. So here on the schematic, we will first create the new schematic, and then we'll click the component library, and then we'll look for operational amplifier, OPAMP. So that's an op-amp. And now this is an ideal single pole op-amp that you are using. And then if we specifically look at it, you have this universal op-amp also that you can use. So if you use this one, it doesn't have a power pin, so we'll go for universal op-amp. That's a linear single pole op-amp with no internal nodes or output voltage range limit. So we click here. We have several tutorial videos on this. So we'll then press escape button on the schematic. After that, we need two power supplies. So we'll go here. We'll say the source, and the source is the voltage. So we want two DC voltage sources. So we'll click here. We'll place them here, because one is a positive pin and one is a negative pin. So here are the grounds that I'm taking from this. And then I will need one input voltage source also. So I can use the F6 on the keypad and then copy this signal. So now I don't have a place here. So let me just adjust it. So I will just select move, and then these two components, I will place it somewhere on the right side of the screen so that I can get, and then I press space bar on the keyboard. So again, I am having a trouble in seeing the complete schematic. So let me place them somewhere bottom. Now it's better. And now I will just press F6. That helps me to copy the components and the devices. So here I have placed that. Now I need a register. So here is the register. I will place Control R. That is giving me that. I need one capacitor. So here is that capacitor. Again, Control R will rotate. And that's it. And now I am able to connect all the components through the wire. So you see now I have made the connections, and theoretical circuit schematic is now being implemented here. So I need two pins to connect here. So let me just write them the way I will connect them here. For example, let me move this resistor R's up there so that all components and the devices are visible. Now I have to connect these voltage sources here to the ground pins, and the top pins are like I will put the label when I will connect them. So you see now I'm step by step implementing this part. So now what I want to do is first complete this circuit. That's the feedback, and then that's my circuit. And here I'm just trying to drag this level to a proper level so that the circuit looks better. I don't need this node here. So that's it. Now it's time to right click this pin. So first let me label them. Right clicking this, I will label, call it as a V plus. So that's the pin, and the same pin I want to place it here, V plus. So you see now, and then right click on this, I will call it as a V minus, and then V minus, and then that's your pin. A same pin goes here. Okay, and now it's time to put the values for the components and the devices. So we've got two voltage sources, we've got the two components, that is a capacitor and the resistor, and we got one universal op amp. What are the properties of this universal op amp? Let's right click, and you see that we are able to set the open loop voltage gain, that is 1 mega, gain bandwidth product 10 mega, offset voltage is 0 volt. So we actually have these variations. We can set them as we want. So for application, we see that these are enough. Then I can set R in, that's the differential input resistance of the operational amplifier, 500 mega. I click OK. Let's say the value of R is 1 kilo ohm. Let's say the value of C is 1 microfarad. And I have a constant voltage of DC 1 volt. For example, I see that. And now it's time to set the DC voltage levels for power supply. So let's set the DC voltage level of this V1 is to be 10 volt, and DC voltage level of this to be minus 10 volt, because we are using the dual power supply. We can use single power supply also, where V minus will be 0 then. And now we have 1 volt DC input, and then we have, depending on the value of R and C, we have that constant. So 1 micron into 1 kilo. So let us write that, how much that comes. So the gain would be, let's say, 1 into 10 to the power minus 6 into 1 into 10 to the power minus 3. No, plus 3. That's the 1 kilo. So it's about 1 into 10 to the power minus 3. So it's in fact it's going to be an attenuator, right? So it's like minus 3. So how about we choose about 1 mega. Here the value for the resistor is 1 to the power 6. So now you will have a gain. So output should be 1 volt constant if we have 1 volt input. Right, so we'll see that by performing the simulations. So the first thing first is what kind of analysis we run. The DC analysis, time domain, everything, but let us run edit simulation card, DC operating point, click OK. place it here and then click OK. So it's going to give you the bias points. The bias points you see here, the output voltage is not labeled here yet. So let us label that. So we'll click here, label net. That's called as VO. It is output. Select that. Click OK. Place it here. Press escape. Press this wire. Make the connections. And that's it. And again simulate it now. So we'll see what is the output voltage. So output voltage is about, let's say, minus 9.9 into 10 to the power minus 3. Output, basically we have a constant voltage, DC volt, 1 volt or 10 millivolts. So the output will be zero. Derivative of constant is zero. And that makes sense. So let us now perform another analysis, edit simulation, and we'll do the DC sweep. DC sweep where I want to sweep voltage source V3, this one. Type of sweep linear, start value 0, stop value 10, yeah, 1 volts, so increment 0.01 volts. See the syntax is ready, click OK, DC, and then simulate. Now I want to see the input versus output. So input is a linear sweep and the output on the same plot is a constant, that is 0. Because your input is constant always at different steps, there is no concept of time steps here. We'll see in the time domain analysis, but now your output is 0 because look at this equation, VO equal to minus RC dVO by dt. So that's why you have derivative of constant is 0. How about we now change this input source to the, so again you have the same signal except that it is sine wave and the phase is not required, 0. Number of cycles 10. Frequency is to be mentioned here, 1 e to the power. So here it is. Now save and now simulate. And now look at this. So your input is green top. This is from 0 to 100 millivolt peak. Output is cosine. So there is a 90-degree phase shift between the two signal. So sinusoidal signal, you have a cosine wave. You again right click, let's say phi is 90-degree shifted. In that category, we'll simulate. Look at this now. This the waveform has changed. If you change the phase, 45 degrees. And now look at this. It is how it is going to behave. So better you kind of say 0. And this is how you will have. Okay. So now differentiators AC response we will simulate. So what we'll do, right click the sinusoidal source, click none, and select AC amplitude of 1, then click OK. Now it's time to simulate the frequency response. It's a high pass filter actually, AC response. Let's say a decade, then number of points, let's say 1000. Start frequency is DC. Stop frequency is about, let's say, 10 to the power 4, like 100 kilohertz. Oh, start frequency is, stop frequency is like 10 to the power 4. Start frequency must be positive, so isn't it? We have like 1. Oh, okay, so we'll create that. So we'll click OK. And now we have to understand what it is like. So let us clear that. Now look at this response. So it has a gain of about minus 8 dB. So kind of you have to increase the gain. Let me use the different color for this. Green would be better. Click OK. So it's a kind of low pass filter response actually. So change the values and accordingly you will have, let's say you have like 1 micron and then simulate, and this is how it's going up there. Here it is, let's say 100K, and you'll see how the response changes again. So maybe let's say undo, and here you change it to 1 micron again, simulate the response. So this is how you can modulate the frequency response of what you want. If you want to make a differentiator like a high pass filter, you have to choose the values of R1, C1 and R2, C2. Okay, so that's all.